Okay, so today we will talk about a new section. In fact, it's a new chapter, chapter 4. Chapter 4 is about applications of calculus. And the first application is something that is going to show up again and again when you're using calculus, which is maximizing and minimizing a function. So what does that mean? So suppose you have a function f of x, and I don't know, let's think about the function f of x as being the so for example, you have a factory of chairs, and depending on how many chairs you decide to make, you're going to have a certain profit. So f of x could be the profit you make as you sell a certain amount of chairs. Let's make it, for example, or actually let's say, for example, the cost of a chair, of every chair for you to make. So if you make a very small number of chairs, you're going to have a lot of fixed costs. Your machines, your employers you have to pay. If you make a lot of chairs, suddenly you run into problems of, you're overusing your machine, you have to do too much maintenance, your machine is not meant to be used for so many chairs. So there's actually, it can happen, right? So there's actually an optimum, like a sweet value, sweet point. Not too few chairs, not too many chairs. That's going to be the optimum situation for your factory. So maybe it's not the best example, but anyway, given a function like this, you may wonder what is the maximum possible value and the minimum possible value of the function. So for example, in this case, say that this is 1, 2, 3, 4, 5. Where do you think is the minimum value of the function?
2.
At 2, right? So this is the min, and the maximum is somewhere around 5, right? Okay, so that's the idea. So x equals 2 is a minimum, x equals 5 is the maximum. And we're going to generalize this idea a little bit today, and I'm going to tell you how to systematically find out what the minima and the maxima are, just to find them. I'll give you a function, and you will be able to calculate systematically what those values are. So first of all, there's a concept that is a little bit more general than maxima and minima, which is the concept of a local maximum and minimum. So for example, let's look at this function right here. This function has 2 bumps, or two hills. Which of the 2 is the maximum? Well, the one on the right? So this is something that you might call the absolute maximum. And this it looks like a max, but it's not really a max, because you see there's other values of x where the function has an even larger value. So we call this a local max. Okay? That means you have to be a little bit careful, because something might look like a maximum, but it's not a maximum because there's other values that are really the maxima. By the way, the plural of maximum is not maximums, but maxima. Okay? And minima instead of minimums. It's Latin. All right, so mathematically, how are we going to define this idea of maximum? What do you think? What mathematical property does it satisfy?
The derivative?
No, let's not think about derivatives for now. Just in terms of the function itself. What is it? The highest y value. That's exactly right. So let's define it. F of x, sorry, f is a function. What is, and let's say that C is in the domain. of the function f. So what is a maximum? C is a maximum if, who wants to say this more precisely, mathematically? I heard some a definition saying it's the maximum y value, the highest y value.
F is bigger than or equal to f(x) in all function.
F of c is bigger or equal to f of x.
X in all the domain.
That's right. Let's give the domain a name. So let's call the domain D. The set D is a set of all points that you can plug in for f, right? We talked about domains before. So f of c is bigger or equal than f of x for all x in a domain. How do you like that definition? Means that every other value has every other x has the smallest y value. Makes sense, right? What about minima? What is a minimum? The converse, what is the converse? F of c is less or equal than f of x for all x in the domain. Okay? Now what about the local maxima and minima? How should we change the definition? For local maxima and minima? Yeah, no. Sorry?
X near to the
Exactly. Okay, so for local minima and maxima, we cannot say anymore that f of c is the largest value because there's other values that are larger. But those values are far away. Okay? So locally means if you just look in the area around, in the neighborhood around c, f of c is the largest value. So local max means that f of c is bigger or equal than f of x for all x near c, and local mean is something similar, that f of c is less or equal than f of x for all x near c. Okay, so what exactly we mean by near? We're going to leave that actually and not too precisely described. Near, think about, it doesn't actually matter, right? You can see that this is a local minimum because if you take points that are sufficiently close, say in this neighborhood over here, then c has the largest value. Okay? F of c is larger than f of x for every x near. If you look at x that are far away, you can get it to be even larger. All right. So there you go. Now, the question is then, when do you have, or how do you find these local minima and local maxima? And there's a theorem called Fermats Theorem. Fermat is the same guy who said another theorem. Do you guys know about Fermat's last theorem?
Yeah.
What does Fermat's last theorem say? X to the 3 plus y to the 3 equals z to the 3, for example.
Write the proof.
So the statement, more precisely, is to say he started looking for integer numbers. Let's say x equals 1, 2, 3, 4, right? Integers. Y integers and z integers such that x to the 3 plus y to the 3 is equal to z to the 3, and he couldn't find them. Okay? And he scribbled in the margin of a book saying, you know, I found this really cool theorem. You know, I believe that that actually has not a solution. It doesn't matter what you plug in for x, y, and z, you cannot get that to be equal to z to the 3. And he said, oh, you know, and I got a proof, but it doesn't fit in this margin, you know, in this book he was writing, right? Well, 300 years later, nobody had still figured out the proof of this thing. And nobody really knew if he actually had a proof or if he didn't find the real proof and made a mistake. He probably made a mistake, but you know, it's still called after him because he was the first one to state it. And he was actually proved about 10 years ago by a guy in Princeton. So 350 years later, something like that, was actually proved, and we now know that that is not possible. You know, you cannot never have x to the 3 plus y to the 3 equal to z to the 3 for x, y, and z natural numbers. Not only that, but it's also true for any exponent larger than 3. For example, x to the 5 plus y to the 5 equals z to the 5 can never be satisfied using integer variables. Anyway, this guy, the same guy, also made a much different theorem. It's probably a simpler theorem to prove, which is called Fermats Theorem, which says the following. Let's see. If C is a mean or maximum or a local minimum or maximum, so any of the points we just talked about before, and f prime of C exists, then, okay, so let me not finish writing this yet. What property do you see that all these values satisfy? Think about it. What is it about the derivative at all these points? Equal to 0. Okay, intuitively it's obvious. You can see it in the graphs, right? Every time that you have a hill or a valley, the bottom is flat, right? That's the first insight in this optimization business, and probably the most important one is that whenever you have a hill or a valley, the bottom has, or the top has, a flat derivative equal to 0. Now, this works not just for maxima and minima, but also for local maxima and minima. That's why we need to think about local maxima and minima too, because they're going to be thrown in as well. Okay? Then f prime of C is equal to 0. Maybe in a moment, if we have time, we're going to prove this theorem, but for now, let's just go with it. Okay? So all these examples that we drew on the board, also on this camera, satisfy Fermat's theorem, because you see these functions are smooth. So f prime of C exists. And as you can see, they all satisfy that. The derivative is equal to 0. Now you have to be a little bit careful. There's a few exceptions. And by exceptions, I don't mean things that violate the theorem. The theorem is true no matter what. But, for example, if the derivative does not exist at that point, then you don't have to have the derivative equal to 0 because it doesn't exist. So, for example, you could have a corner like this, in which case this guy is the mean. And it does not satisfy that the derivative is equal to 0. Does that violate the Fermat's theorem?
No.
Okay, you should realize it does not violate the theorem because one of the assumptions is that f prime of Z exists. So here, f prime of C does not exist. Okay, that's why you cannot say that the derivative is 0, because simply it has a corner. It doesn't really work for this system, for this example. What about this function here? This is a function, I don't know, f of x equals x to the 3. Okay, it becomes flat. It becomes flat at this point, but then it keeps going up. What's going on there? First of all, is that a maximum or a minimum?
No.
That is not a maximum or a minimum. So this is not a max or a min. But the derivative is 0. So what's going on? Let's see, is Jesse here?
Yeah.
Jesse, what do you think is going on?
It's a point of inflection.
It's a point of inflection, that's right. So the function does like this, it becomes flat, and then it goes up again. Does that violate the theorem?
It's not a minimax. So no.
It's not a minimum max, exactly. So you're absolutely right in that you have to look at the implication the way it is. If it's minimum max, then the derivative is equal to 0. What the theorem is not saying is that if the derivative is equal to 0, then it's a minimum max. You see, they're two different things. So you have to be careful with which direction you take this implication. You're going to be very soon you're going to all be writing derivative equal to 0 and finding x and y and then saying, okay, that's the maximum and min. But you have to be a little bit careful because it's possible, just because the derivative is 0 does not mean that it's a maximum or a minimum. Because the implication goes one way. So I'm going to write here, this is an example showing that f prime of c equal to 0 does not imply that you have a min or a max. And I really should not say exceptions. I should say more like warnings. These are not exceptions to the theorem. The theorem is true no matter what. Okay. Let me give you an example of this situation, and then we'll talk a little bit more about the wrinkles of this problem. So example, f of x equals 3x squared plus 12x minus 5. Find the min and the max. Okay, so for the solution, you point out that f prime of x exists for all x. Okay, so the second assumption of the Fermats theorem, f prime of c exists, is always satisfied. We don't need to worry about that part. Okay, and now we can set f prime of x equal to 0 to find such points that the derivative is equal to 0. That means that 6x plus 12 is equal to 0. Because the derivative of this function, of course, is 6x plus 12. And then we get 6x is equal to minus 12, or x equals minus 2. Now, are there any other maxima or minima?
Nope.
There cannot be any more maxima or minima because they all have to satisfy that the derivative is 0. Right? So this is the only potential minimum and maximum, or maximum. Why do I say potential? Because once again, because of this second exception, just because the derivative is 0 does not mean that it's a minimum or maximum. But this looks like a parabola. This function looks like a parabola, right? X squared plus something plus 5. Looks like an upwards looking parabola. So intuitively, at this point, we cannot be too much more precise. Intuitively, this guy is what? Minimum or maximum?
Minimum.
Minimum. Is it a local minimum or an absolute minimum?
Absolute.
Absolute minimum. Since the function looks like parabola, upwards parabola, x equals minus 2 is the absolute the absolute minimum. So you have to be a little bit intuitive about it. It's not enough to just mindlessly derive equal to 0 and say, okay, that's the answer. You need to think a little bit more. And this theorem is very useful to narrow it down. You narrow it down to minus 2. I mean, just by looking at it, you wouldn't have thought of minus 2, right? In fact, you would first have to figure out how the function looks like. But using this theorem, you derivate, plug it as equal to 0, and then think a little bit to confirm your suspicion. All right. So now let's talk about other situations where the answer is more complicated than what we just said. Some other situations. For example, you could look at f defined on an interval d is equal to a comma b. So do you guys remember this notation that of the square brackets versus the round brackets? We're going to use that notation now. Square brackets means that the points a and b are in the domain or not in the domain?
In the domain.
They're in the domain, that's right. Okay? Is that clear to everybody? This square brackets means that a and b are part of the domain. They're points where the function exists. Okay. So now we're not thinking about a function defined on all of the real numbers, but only on that interval from a to b. And what can happen now is something interesting, which is that the function might actually have a maximum or a minimum that does not have derivative equal to 0. What is the minimum of that function over there that I drew?
A.
It's a, right? Do you agree? Does the derivative at a equal to 0? No, in fact, the derivative at a doesn't even exist, because we really kind of need space on both sides. You could think about the derivative from one side only, but we haven't talked about that. So we really don't quite consider, right now we're not considering the derivative at the endpoints. Okay, we're just thinking about the endpoints as endpoints. The point that I'm trying to make here is that if the function is defined on a bounded interval from a to b, the max and the mean may well be on those endpoints. So in this case, the max is up here. The max is up here, and sure enough, the derivative at that point is 0. And the min is down here, where the derivative is not 0. What about this point here? What is that?
Absolutely nothing.
Mi says absolutely nothing. Actually, it is something. It's a local max. That's right. Okay. In that case, if a function is defined on the interval d from a to b, you have to be careful that the minimum and the maximum might be a or b. It doesn't have to be, but it might be. So you have to take those points into account. Now, we also said that just because the derivative is 0 doesn't mean that it's a local maximum or a minimum. And I'm just saying right now that just because it's the endpoint doesn't mean that it's a maximum or a minimum. Okay, so the ways to systematically approach this problem is to narrow it down to a few points that might be maxima or minima, and then look at those individual points and see what happens. So it's a little bit like you're choosing a president, or you're having an election. You say that we're going to have a calculus class student president, okay, among you guys. Okay, so probably one of these guys are going to be signing up, Ms., right? So before you have a president, you have to have a bunch of candidates. So you first narrow it down to a small group of people, the candidates for president, and then you choose from those which one is actually going to be the president. Okay? So we're going to be something like that. We're going to be doing something like that here. There's a lot of points from A to B. There's infinitely many points, but there's only a few points that are candidates for maximum or minimum. Those candidates for maximum or minimum include the endpoints and all the points where the derivative is 0. That is not to say that those are, all of them are maxima and minima, but they are candidates. Okay? So the way to approach an optimization problem is to narrow it down to the candidates first. So strategy, narrow down the problem to points C that are candidates for mean or max. And so I'm going to give you a definition. So f is defined on domain D a critical point the official definition of this thing is not a candidate for MaxMin. It's called a critical point is a point C such that either f prime of C is equal to 0 or f prime of C does not exist, or in case that D has this shape, include A, B as critical points. Okay, so there you go. So now we're essentially embodying these arguments. There's a lot of points that for sure are not maxima and minima, and we can rule them out. But all the maxima and minima, whether absolute or global or whatever, they're going to be candidates, and they're going to be critical points. So either the derivative is 0, or sometimes you're going to get some kind of corner. Okay. By Fermats Theorem, the maxima and minima and the local maxima and minima must be critical points. Okay. So let me give you an example. F of x equals absolute value of x defined on D equals from -1 to 2. Find all critical points and find the max minimum. All right, so what does the function absolute value of x look like again? It's like this, right? Like a v. Okay, and we're defining it between -1 and 2. So I'm going to draw it only between -1 and 2, like this. Why do I draw those balls on the ends? What does the ball mean again?
That they're included.
Okay, the balls means that these points are included in the domain. The point 2 is part of the domain. The point minus 1 is part of the domain. Okay, now let's look at the definition of critical point. Critical point is a point C such that either the derivative is 0, or the derivative is not defined, or it's the endpoint, A or B. So do you see the different critical points in this function? What will be a critical point? Let's see, Jeffrey? Well, what are the critical points? Ah, okay, that's fine. Mari?
Yes.
What are the critical points?
The 2 endpoints
Okay, the 2 endpoints?
and then 0.
And 0, perfect. Are there any points where the derivative is equal to 0?
Yeah.
In this case, there are not points where the derivative is 0. Great. So the critical points are minus 1 and 2. These are the endpoints. Endpoints. And also x equals 0. Because f prime of 0 does not exist. Okay, now what? Now that we narrowed it down to the critical points, now we look at each of the critical points much more closely. And just by looking at those points, we can figure out whether they are minima, maxima, or local minima or maxima or nothing. So how do we find out what is the maximum of the function? Well, since we know that the maximum has to be a critical point, it has to be one of those 3, right? So imagine that you didn't know, imagine for a moment you only know the critical points and you don't know how the function looks like. Then what do? What about people in the back? Or in back meaning the second row on. If I didn't know how the function looks like, yes?
Would you plug in the critical points to the original function you have?
That's exactly right, yes. If you don't know what the function looks like, you look at the critical points and you evaluate each of those critical points. And the one that has the maximum value for f, that's the maximum. Okay. So you evaluate f of minus 1. F of minus 1 is 1. F of 2 is 2. F of 0 is 0. And you can see that this one has the maximum value, so this is the max. And f of 0 is 0, so it has the minimum value out of the 3, so this is the min. Okay, so you look at those critical points, you evaluate them, and then you know which one is the maximum and which one is the minimum. All right, now finally, I'm going to mention some other situation that may happen, which is that, so question, do min, max always exist? So this is something that we may not have, we haven't talked about it before, but we seem to be assuming that they always exist, that there's always a min and a max. So let's see. Suppose that you define the function f of x equals 1 over x on the interval, let's say 0 to 1. But there's a problem with 0 to 1. For x equals 0, this thing is not in the domain, right? For x equals 0, f of x does not exist. So let's define the domain to be 0 open, 1 closed. That's really the only way I can define this domain, because the function at 0 doesn't have any value. What does that function look like? The function looks more or less like this. Well, not quite. Let's say this is 5. Okay, fine. Now it looks like that. All right, so now what? What is the minimum and what is the maximum? What do you think?
There is no maximum.
There is no maximum, I hear. Do you agree? Is there a minimum? There is a minimum. The minimum is at x equals 5. This guy is the minimum. But there is no max.
Could the max also be infinity, or?
I hear a question. Does the max is the max equal to infinity a valid maximum? And well, in this case, I mean, even if we allowed infinity to be a maximum value, we don't have an x value. We don't know what is the value x such that f of x is infinity, right? It doesn't exist. The only point you would have to set equal to 0, x equal to 0, but if x is 0, it's not even in the domain, right? So it's a good idea, Miss, but it doesn't work in this case. So, I mean, you could define f of 0 equals infinity, and then it would be okay. But then we would have to define the function outside of the real numbers. Okay? So this is just to make you aware that the maxima and minima do not necessarily exist. Let me give you another example where the maxima and minima do not exist. F of x equal to, and then let's just say I don't know, x squared minus 1 defined on the domain minus 1 to 2. But notice that I'm making round intervals from minus 1 to 2. So how does this function look like? It's basically a parabola. It's been shifted down by 1. And it looks more or less like this. But the function is defined on a round interval from minus 1 to 2. That means that minus 1 is or is not in the domain. It's not. So I draw an empty ball at minus 1, and I also draw an empty ball at 2. Now, what is the max of this function? Well, the max of this function does not exist, because it would be 2, except that 2 is not in the domain. Right? Okay, so that's another situation. It's a much less contrived situation than this one, but still the maximum doesn't exist. All right. So that means that we really have to define the function on closed intervals. Yes?
Are the open intervals, does that mean that the critical points can still exist there?
The critical points have to be points in the domain. So if the function is not defined on that point, it's not in the domain. It's not a critical point. Yeah. Okay. So that means if we want maxima minima, we better include those endpoints. Okay. But just including the endpoints does not guarantee that the function has a maximum or a minimum. Because you could have another example such as this one. Well, let me just draw the function, just to make the point that even if the function is defined on the interval from, let's say, from 1 to 2, or from 1 to 4, you could still have a function that doesn't have a minimum or a maximum. How can that happen? you could have a function that is certainly defined here. It is defined here, but it doesn't have a minimum or a maximum. What can happen in the middle? Let's say that at x equals 2, you have this thing. Okay? And I don't know, the function has the following value at 2. The value at 2 is like down here. It's a funny function, right? But so what? It's a function. It's defined on the closed interval from 1 to 4, and it doesn't have any maxima or minima. It only has local maximum and minimum, this one right here. So these guys are no max or min. So what happens with this function? What's wrong about this function, or what's the problem with this function? It's not continuous, right? Okay, so this leads us to the second theorem, which is basically a little bit laying the groundwork on when the maxima and the minima really exist. And that is that the function has to be continuous, and the function has to have the endpoints of the interval. That's going to be our second theorem. Let me write it down. And this is called the extremum, or the extreme value theorem. It makes it sound like it's some extreme thing, like an extreme sport, but it's not really that extreme. Extreme value is just a funny way of talking about minima and maxima. Minima, maxima, local maxima, those are all extreme values. So the extreme value theorem says that if f is defined on a closed interval AB and is continuous, then it has, or it attains, min, well, let me say it a little more precisely for the theorem, an absolute minimum and an absolute maximum. Of course, there's different points. It's not the same point. It has an absolute minimum at somewhere and an absolute maximum somewhere else. So if I have the function defined from A to B, and it's defined at A and it's defined at B, it doesn't matter how the function looks like. And it's continuous. It doesn't matter how I wheel it around. It doesn't matter whether it's always pointing up and the maximum is on the endpoints or not. It has to have a maximum and a minimum. Yes, Mary?
What if it's just a straight line?
Okay, what if it's a straight, you mean a horizontal straight line?
Yeah.
Okay, that's a very good question. Let's go back to the definition of maximum and minimum. So the definition of maximum and minimum means that it's a maximum if it's a point C such that f of C is bigger or equal than f of x for all x. So if the function is a straight horizontal line, that means that there is no maximum or there's a lot of maxima. Means that there's a lot of them. In fact, every single point satisfies the definition. Okay? So that means that the theorem is still true. It's just that everybody is going to be a maximum. In fact, everybody is also going to be a minimum. Equality, yes. Right, so this is the situation. You have a continuous function from an endpoint to an endpoint. Then you have to have a maximum and a min. But notice that the max and the min might be the endpoints. Okay? All right. And with that said, then you can start looking at all kinds of functions. I'm going to leave that to you guys. You can set equal to 0, find the critical points, and then find out of those points which one is the maximum and which one is the minimum. Do you have any questions? No questions. Okay, great. See you next time.